Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right, it gives me great pleasure to introduce our next speaker, Doug Lange, who is going to tell us about trust of, in, and among adaptive systems. Very interesting topic. Hi.
Thank you. So I don't get the fun that some of you have of diving in very deep into one particular area and really creating it. But what I do get the fun of doing is finding lots of different technologies, approaches, and applying them to problems that the U.S. Department of Defense has. And so what I'm going to talk about are some problems and some possible approaches that we're exploring, just beginning to explore in most cases, and talk about what our view of adaptive systems is, because this view is going to be a little bit different than what some of you were looking at. The systems I'm talking about are going to change behavior fairly radically after they've been deployed, and we have to look at what technologies we need for that purpose. So I started looking at adaptive systems quite some time ago in a small way, and got more and more interested in it and became more and more involved in them. And at one point I had a discussion with a woman who was in charge of certifying systems to put on naval ships. And I said to her, I'm going to deploy a system, and it isn't going to do all the things it's going to eventually do when I first install it. It's going to change behavior, and it's going to pick up capability as it's being used. What do you think of that? And the words she said to me, I can't repeat since we're being recorded. But it's not something that we're really set up to do. So what are some of the areas where we're going to see this kind of radical adaptation? The first is in autonomous vehicles. We're working on using teams of autonomous vehicles to perform a variety of duties for the Navy. The other services are looking at them as well, and we're looking at joint capabilities among the services. And these systems are going to work in areas where the threat that they're dealing with changes over time. The tactics of the people we're trying to protect ourselves against changes over time, and so the tactics that are employed by these systems in order to track, in many cases the idea is to be able to track the possible threats in an area. Another area that I'm going to talk about is service-oriented architectures for what are getting called ultra-large systems of systems. That's not my term, that's one that I learned from some collaborators at UCSD, University of California, San Diego. And here we're talking about our command and control systems, which are becoming increasingly large networks of capabilities that, again, change over time, not just necessarily each individual component of it, but as we put new capabilities onto this network, in a variety of ways, the overall behavior of the network changes. And we have issues about security, performance of the network, ensuring that client software is getting the right information depending on which service they're accessing. So we have some very interesting problems there. And the final area I'm going to talk about is task learning. I've been working under the PAL program, Personalized Assistant That Learns, from DARPA. And one of the key capabilities that was being explored in PAL was the idea of task learning. And here we are, in fact, fielding software where the software doesn't do all that it's going to do once you field it. The users actually teach it to perform new tasks. And we have to look at what the implications are for fielding systems like that. So the Department of Defense and the Navy isn't really set up for fielding systems that change behavior. We work very hard to build systems that behave consistently so that we can verify that they work properly and safely in a mission critical and dangerous environment that we work in. And now we're really talking about introducing a lot of adaptation. So the workshop challenged us to look at adaptation perhaps under the same sort of aspects of evolution. You know, the fact that there are creatures that have evolved to be very secure in their environment. And I want to turn that a little bit on its head and say, well, there's also a lot of creatures that went extinct. And natural selection works, but it also leaves behind a lot of creatures along the way. And we don't have the luxury of fielding a system in a military environment and just sort of seeing if it's going to survive to be the next generation or not. It can cause injury or death if it's in a safety critical situation and it's behaving badly. But not adapting is risky. Ferris Bueller, not all of you are into American movies, I'm sure, but there's a line in a fairly famous American movie that I've twisted around a little bit. But the military environment moves pretty fast. The threats change constantly, and if we don't adapt, the systems will change too slowly. Sending systems back to the programmers every time we want to update our tactics, update our capabilities, just isn't feasible anymore. Okay, so I'm going to talk about autonomous vehicles for a minute, few minutes. Currently, when we field an unmanned vehicle in the military, it takes a ratio of many people to one vehicle to operate it. So that doesn't seem to have a lot of benefit from the standpoint of it being unmanned, other than perhaps the fact that where the vehicle is going, now we don't have the risk of one of our airmen or sailors or infantrymen or something if we're going to clear out some mines or improvised explosive devices. But we need to flip that on its head because we want to have teams of teams of unmanned vehicles. And so these vehicles have to really raise their level of autonomy a great deal in order to make that happen. We need to have a single person be able to operate many vehicles, which means we have to have those vehicles adapt. We have to look at what information we bring back to the human manager of these vehicles, at what degree of abstraction we're going to show that information, so that one person can keep track of what's going on with many vehicles. And these vehicles are going to have to have complex behaviors and decision making, because we're not going to be able to use a joystick to control all 10 or 20 vehicles that a single person might be controlling. And so we have to describe these vehicles in terms of these complex behaviors. And if we're going to have these if we're going to have these systems adapt over time, they're going to have to be adapting complex behaviors. So an example I'm just going to briefly mention is that at Stanford, they've been teaching helicopters to perform maneuvers rather than programming them to perform these maneuvers. And they get better performance out of the vehicles that are taught than the ones that they program. And in this case, what this diagram shows in the black is the maneuver with this helicopter. They're trying to have it shift back and forth, I believe, while it's pointing down and move back and forth. And they are able to get it tighter on the maneuver that they taught, and the other ones are experts even controlling the helicopter and also programs behaviors. So one of the things that we believe is that to get complex behaviors, autonomous vehicles are going to have to learn these behaviors because they just are too hard to just program them in. So imagine having multiple vehicles learn tactics probably through some sort of simulation. And we evolve these tactics over time. So for instance, this comes from a video game. It's a research video game, not one that's marketed, called Nero, that came out of the University of Texas, and Dr. Stanley's now at University of Central Florida. Nero allows a user to send out a group of agents to do a battle. And it's kind of a capture the flag sort of game, although there's incoming fire. And see how they do. And then pick the robots, the simulated robots that are behaving in a way that seems beneficial. And evolve these tactics over time because they'll spawn a new generation and use evolutionary programming techniques to eventually create a generation of these robots that the user feels is effective, and then two users go and battle each other and see how they did after they've trained them in tactics. Well, we believe we're going to have to do something very similar, and in fact, perhaps use the neuroevolution techniques that are used in this game. And we can do that through simulation. We could send out simulations of vehicles, see if we like their behaviors, update those through evolutionary means, and try to develop tactics that work. But it is quite possible that these vehicles will learn the wrong things. For instance, the vehicles that win might be incredibly bloodthirsty and violent. Maybe the right way to track, maybe the way to score best in tracking a target. Even if we don't weaponize these vehicles or anything, we send them out for reconnaissance purposes. They have sensors on board. Well, one of the easiest way to keep track of them is probably just attach yourself to it. So just run right into it, and you'll never lose it. Well, that's not a behavior that ultimately we want to have expressed, but it could be that through the utility functions or something that the ones that do the best have some sort of quirk in their behavior that we really don't want to have expressed, and we need some protection against that because over time they might learn the wrong things. In addition, the other problem is we have limited human understanding of how these behaviors are going to be seen in the future. When we send these vehicles out the next time, are we really sure we know what they're going to do? Well, it's hard to prove that. It's hard to have a lot of trust in what those vehicles are going to do when they adapt. Even if we use a different kind of learning. There are many kinds of learning. The type that Stanford's using is not this neuroevolution approach. It's a reinforced learning approach. So there's a variety of different learning capabilities, learning techniques. But in all cases, we're not going to be able to prove them to be correct in any way in a safety critical situation. So what happens if we maybe put some protections on this? I go back, way back to when I was taking my first software engineering classes in undergraduate. I was taught by the professor, one of the few things I remember him saying was that aircraft systems, have to have redundancy because if something fails, you don't want to fall out of the sky. And one of the strong things to do is have perhaps an odd number of these systems, and they can vote on whether or not something's going on. And sure enough, that same technique is still used today. If you look at NASA, they use that in space missions. Sometimes five computers running simultaneously, and then they have a failback system so that as they lose them, there's still some means of using that redundancy effectively. But we don't want to just replicate the same system if the risk, in fact, is in our technique for how to develop it. We don't want to use the same learning algorithm 3 times. We'll make the same mistake 3 times. So the idea that we've presented to the Office of Naval Research and others is to look at a triple redundancy, but with three different methods for controlling an autonomous vehicle. So the first one might be machine learning. So we'll learn tactics and we'll take a chance on what it is those systems are going to learn. But at the same time, we can program in some invariants for protections. And there's a few that we can understand well enough that we can probably protect using. And then the final one I'm going to call introspection. I'm going to show you an example of it that's called an ethical adapter, which is a little dramatic, but I'll show you something about that. So this work that I'm going to talk about comes out of Georgia Tech, and it comes from, it's inspired by the type of ethical training that soldiers are given in the U.S. Army and in other services as well. And basically, soldiers are taught you have to look at not only the tactical benefit of your actions, but you have to look at what some of the unintended effects might be. Who else is going to get hurt? And is it something that's against the rule of law? But even if it's legal, is it something where the consequences, negative consequences, may outweigh the benefit of the action? And they're taught that they have to go through this process when making decisions. So what about autonomous vehicles? So it's getting a little bit Isaac Asimov here, but it's actually being experimented with. At Georgia Tech, they're experimenting with something called an ethical adapter. Now, if you look at how it's being implemented, what it really is an introspection sort of method. When they're going to make a decision, and they're thinking in terms of weaponized autonomous vehicles. If they're going to make a decision about attacking something, there's a decision process has to be gone through that makes a prediction about what the effects will be. Is there a possibility of collateral damage? And what's the probability of that? How is this an appropriate weapon to use in this situation? And then the system makes a decision about whether or not to actually pursue that course of action. And then the next step is that the battle damage assessment actually has to get reviewed to see if the autonomous vehicle predicted well. So what happens if there was collateral damage and the prediction was that there wouldn't be collateral damage? Well, now the vehicle really should, in some ways, think, well, I'm not doing a very good job of predicting this. And that's what this ethical adapter tries to do. The vehicle gets more and more restrictions placed on it, the worse it's doing in predicting the outcomes. So if it's predicting well and making good decisions, the vehicle allows itself and the human manager and the check systems that they propose for this, and this is all strictly simulation at this point, but the check the check systems will allow it to go ahead and make decisions to fire a weapon. If it's not doing a good job, if it's predicting too low in terms of collateral damage, then restrictions are placed on it that it's not allowed to make decisions about certain weapons. And those restrictions get more and more severe as its prediction ability is found to be less accurate. So we could put something like this as one level of redundancy and go with learning, but have an ethical adapter. And I won't describe invariance because I know all of you know all about just programming in some invariance. There's nothing interesting I'm going to be able to tell you about that. So we're actually proposing to put this all into a simulation capability and do some experiments on it. And we hope to be able to report out some results where we can take something like Nero, play the game, but attach an ethical adapter and some invariance to it and see what happens when we have this redundancy. So the next area I'm going to talk about are these ultra-large systems of systems using service-oriented architectures. The Department of Defense is moving to what we call network-centric operations. Everything's about the network as opposed to individual capabilities. And these are being implemented using service-oriented architectures. We wanted to decompose the capabilities into small chunks, make services out of them, expose data wherever possible, and dynamically compose capabilities out of the individual services. So obviously, and this is one of the keys of service-oriented architecture, services get used in ways that weren't intended when the service was initially created. So that's a form of adaptation. We can add new capabilities that use services in novel ways and add those to the network very easily, but we can have an impact on the network itself. It's actually quite possible because the Navy in particular has communications issues, talking from ship to ship, for instance, where we call them thin pipes. There isn't always a lot of bandwidth available to some of the smaller ships, for instance. So it's quite possible to place a new capability on the network that you've composed out of these services and do it badly and essentially create your own denial of service attack on yourself. There are also ways of corrupting the information that's being passed from place to place by replacing a service with another one that has the same interface, obviously, but maybe has different semantics of how it goes about doing things. So there's some interesting problems to having this kind of system adapt after you've fielded it and have the consequences ripple down through the capabilities. So I started looking at this way back in 1997 because I was involved in an exercise in Australia that was a multi-nation military exercise. We have all these command and control systems in place that are good for communicating among aircraft and ships, and it's a live fire exercise. So they're really going to go drop some bombs at some range, and there's all this incredibly complex maneuvering of ships, aircraft, people, other vehicles going on, and the number one concern in the entire exercise was not damaging the Great Barrier Reef. None of our command and control systems were set up to protect the Great Barrier Reef. So clearly we needed to compose some new capabilities that didn't exist, and we didn't have that capability. So it was all a very manual process at that time, and it was sort of one of those aha moments that our systems have to adapt to do things we didn't envision when we developed it. So one of the other big issues was medical evacuation. This was going to be a dangerous exercise. They were expecting real-life injuries because we were moving lots of people. They were going to land on beaches, jump out of airplanes, and drop real bombs somewhere. And we needed to make sure that if people got hurt, we knew what to do with them. Well, as it turns out, one of the big risks with doing an exercise like this in Australia is the fact there's an enormous number of venomous creatures and wild things like tapeworms were a problem, but poisonous octopus and variety. There were all sorts of wild injuries that had to be dealt with during this exercise. So we had created a system for keeping track of patients and their evacuation through the process. And it was all web-based, and it was one of our first forays into a completely web-based system. And we were tracking all this really well. But it wasn't service-oriented architecture in any way. I mean, that was a bit before that was cool. And there were lots of problems with the semantics of reporting cycles and whatnot in the way we did it. And what we found is that the questions that were being asked, again, weren't the ones that we were originally set up to answer. Because we were told, here are the things we want you to be able to answer, but here were the real questions that came about. So we decided that we really needed to compose new capabilities on the fly based on the questions. And so we set out to automatically generate services after that, well after that. But and the picture down here is an experiment that we did where we were able to state a goal in a language that would be the goal of the information. Pull out web services that were described in OWL-S, put them through a composition planning engine, and actually pump out BPEL, the business process execution language, capabilities, and put new capabilities on the network, all automatically, all at the toy problem level. Okay, so we didn't do anything large, but we could, in fact, redo this scenario where we were able to rapidly compose web views of data that were for questions that weren't asked ahead of time about medical evacuation and where the field hospitals were, which ones had beds available, things like that. So that's the sort of adaptation that we need to be able to do for the network-centric capability. But here's the problem. It can take months to put a new piece of software on a military network because it has to be evaluated for safety and what it's going to do to the rest of the network. And it's a very complicated process. Well, now what happens if we put a generation system that's going to generate new services on the fly based on what the users are asking for rather than even sending it back to the programmers? Is that going to be safer or more risky? It's possible that one solution is to build really good tools so you know that what you're putting in there is safe. But there are other possibilities of just improving the process by which we put new capabilities onto a network and allow the network to adapt. So one possibility is, rather than having a very binary process of whether or not we allow something on the network, to have a graduated process where we can have, and this is just a wild, one first approximation of what we could do, but have just a set of levels that talks about some of the amount of testing that this particular new component has gone through, and so we could say with levels 0 through 4. And where at first maybe at level 0 we were at least sure that it wasn't a virus that we created, or something like that. And we'll label these services according to this with some sort of broker that will keep track of what level each one has gone through. And as real people back on the lab see that new services have been added to the network, they can put them through a testing process and really ring them out. And as they pass, they can get a higher score. So one of the possibilities is to use a policy language and create a broker system that's going to be based on this policy language, but turn it inside out. This is an example out of MIT where policy languages are being used to deal with access control. So a client wants to get an image where there's a policy for who gets to see this, and it's described in the policy language. And there's inference that's done about whether or not this person should have access to it, and ultimately the client either gets the image or doesn't. We need to turn this around, turn it inside out, because now what we want to do is say, I'm a client piece of software, and I need very detailed, very trustworthy information. I'm in the planning process. I'm not in a hurry. Give me something that definitely has been certified to the highest level, and I want to go find a version of the service that exists that has that level of security attached to it, that level of trust. And that's what I should do. Or maybe I've just generated a new service, I'm in a hurry, I need this information now. Anything that's gone through level 0 that we know at least isn't going to blow up the system, I need this data right now. I can't wait for someone to go check it out in the lab, and I'll go access that. So the trust has to be on the other side. Now the clients of services need to know how much to trust these services for the information that they're after. And so this is, again, just the start of an effort where we're trying to turn the policy inferences inside out and try to experiment with such a network.
More sophisticated mechanisms such as trading or speed of obtaining the data against how trustworthy the data would be.
Right. So we can specify the same way how much we know about performance, and there are languages already out there. I can't remember the reference to the one I was looking at the moment, but there are languages for specifying here's what the performance you can expect from this service, and fill that in. Beyond the normal sort of interface definition of here's the data you'll get, here's the query you have to give.
Yeah, and is there an element of cost involved as well, or you do not worry much about cost?
So on this sort of network, cost is really just in how much of the network I'm eating up. We own the whole network, so there isn't the other forms of cost.
Yeah, but you might be competing with various clients. Some of them might be
higher priority
than others.
Exactly.
And therefore you might restrict usage of a high-level service to
Right.
high-priority clients when they are around.
That's true, and that's actually not the area I'm interested in, but there are people doing that kind of work in the DoD. I'm sure it's happening outside the DoD as well, but DARPA in particular has invested a fair amount of research money into that kind of prioritization scheme into networks. So the final aspect of adaptation I'm going to talk about comes out of the DARPA PAL program. And this is what I've spent the majority of my time on for the past several years. This was one of DARPA's major investments in machine learning and artificial intelligence over the last several years. DARPA periodically makes these big investments in certain things. And this was a 5-year program where the idea was to create more intelligent behavior out of software that was going to act as an assistant to a decision maker by integrating multiple machine learning technologies together and trying to come up with new machine learning technologies. So you're supposed to think of this as your secretary in a box. And in particular, there were 2 major groups under the PAL program, one out of Carnegie Mellon. Their program was called Radar, which was underneath PAL, and one out of SRI International, which was called CALO. And we got involved from the evaluation and the application aspects of the PAL program. But the idea is that the system has to adapt to different users, missions, threats. The environment changes. You need to be able to adapt to it, and do this all without reprogramming the system. So one of the areas that's most interesting out of the PAL program had to do with task learning. And the reason I consider it most interesting is because it's the most radical adaptation that PAL was involved in. Because here, like I said, we're fielding systems without them being fully capable, which is an odd thing to do. And then we're going to expect it to learn in the wild, is the phrase used, the capabilities needed to help the user do his or her job. And there were a variety of different task learning technologies that were created. The one that we played the most with is Lapdog, where you can teach the system to do a task for you. And it's not strictly just a macro that's being built. There's a fair amount of inference underneath to sort of generalize on the task that you've created and allow it to work with different inputs, different situations that are similar but not exact to the one that you've specified. It uses a combination of natural language capabilities as well as activity recognition of what you're doing with the keyboard and mouse, but also you're also telling it what you're doing, and it's got a vocabulary and natural language capabilities to reach back to an ontology and figure out what's going on. And so this is the in many ways the biggest threat to this sort of status quo of how to field systems in the military, because this is where I told the woman who was in charge of certifying systems for the Navy, I'm going to field a system before it's fully capable and allow it to learn to do its job. And that's not something we're accustomed to doing. So yes?
Systems that could touch weapon systems?
Well, we have not experimented with that in any way, and no one's really suggested that. These have been for information systems, for decision support. But you can think of, but any time a military decision maker is making a decision, it ripples down perhaps to a decision that has to do with weapons, right? So you care about these things, even if they're not touching the weapons directly. We care about the information that the decision makers get, and ensuring that the decision makers understand that information, know where it's coming from, and have trust and can decide how much they trust that information in their decision making. And adaptive systems threaten that, because trust is often achieved by having consistent behavior. So these are some ideas about what happens when you put systems that do this very radical adaptation in place. If I create a new task on the system, or I put a system out there that needs to learn and be taught by the user to do something, I actually expect that the user's performance initially goes down, because now they're spending some time teaching the system to do something for them. And hopefully, performance goes back up and ultimately gets higher than it was before, otherwise the system wasn't very useful. But so that's the expected scenario. But you can also imagine a couple other scenarios. So the user starts with the system, it's not learning, it's not things aren't working out, abandons the system, so now his performance is back to where it was in theory. Or the worst case scenario, the user continues to try and try and try, and performance goes downhill and never improves. So we tried to look at, well, what would it take to ensure that a system like this would be successful, and we would get that sort of standard learning curve that everyone looks for, and not be abandoned or a disaster. And so the idea was that we should have a boot camp for these systems. That we don't send sailors out to sea without teaching them something first. They have to have some background knowledge that allows them to learn. So that ontology underneath that task learning has to be rich enough that the tasks actually can be learned. So there has to be a certain amount of background knowledge in these systems, and it's not always something that's going to be programmed in by a developer in the plain system prior to it being fielded. So the idea would be to take these systems, put them in a simulation environment, and allow some training of them in a simulation environment first, and then put them out in the field and see what we get. And so we modeled, yes?
So just on that, can you share learning amongst your devices? So
yes. There were some experiments in the PAL program and some discussions about how assistants share knowledge. None of the ones that we have deployed at this point, and we've done some experimental deployments of PAL technologies, really do that sort of sharing of the knowledge. But the theory's there, right? Because, I mean, at the very worst, you can just replicate the knowledge and put it out in a lot of places. So that's trivial. Now, can you do something a little more sophisticated and merge the knowledge of them? And I don't think anyone really got there into much in the way of experimentation. Yeah, there was some experimentation of that, I believe. That's not something I know much about. So we modeled the environment that these would be working in. So the task learning engines basically had a very familiar sort of task representation. You could have tasks and then methods underneath those. And methods, you could choose a method to do a task, and then underneath that are more tasks. You have to do all those tasks to achieve that method. You can decompose tasks this way very easily. And then so you learn new tasks or methods by appending them onto this tree. And then there are background concepts that are needed for these tasks. And so you can imagine a concept being associated with tasks so that they can be achieved. And so then ran some simulations based on that and tried different algorithms in terms of how the humans would behave, in terms of training the system, spending time to train the systems ahead of time, how much of the environment was observable to the learning systems. So Lapdog has, and the activity recognition has to be able to instrument certain capabilities in order to learn from them. So the question is, how much was observable? What sort of human behavior was there in working with these assistants? And then finally, how much preparation and what strategies of preparation were used in putting the system out before fielding it. And we came up with some interesting results about what was going to be important about how we trained and how we behaved using them. So here's one that I kind of like because it has the graph ends up looking exactly like my proposed graph originally. But basically what you see is there's a threshold that until you get to certain thresholds, you get the disaster in observability. So enough of the system has to be observable for it to be happening. So none of these results are counterintuitive, but it was interesting to see which ones, at least in this simulation, were more relevant than others. This was different strategies for how much time the user actually took in going through the training procedure, using something like Lapdog to teach tasks to the system, and I should say that the simulation had a big string of tasks that had to be performed, and there's a scoring mechanism for how well tasks were getting performed, how far behind the user was getting on deadlines, or how much spare time was being built up. And this last one is actually a spare time chart, which looked at and it's just one of many of them because there's lots of different comparing the preparation with the observability and combining all these. But different strategies for preparation, how much you knew about the domain and targeted the preparation in that domain as opposed to randomly trying to teach within the broad domain, how that would go. But the only point I wanted to bring up here was that if we look at adaptability in terms of machine learning, then we have to look at how we train our systems, much like we look at how we train our people. And that's it.